So the starting point is the following equation, namely the one that defines the Gauss curvature on S bar. So that's our starting point. And the idea is to now pull back this equation by F star. By F star. Then we get, of course, also an identity. First, let's start with the left-hand side. So the left-hand side. So we would like to analyze what the pullback of F star of D of the connection form is. So now we use, the first trick is D and the pullback, they commute. So what we have, the first one is D of F star connection 1, 4. Now we use our lemma that we have up there, is that the connection form on S bar, if you pull back, you get like the connection form on S. So this gives us d omega 1, 2 by 0.3 of the previous lemma. But if you know, like d omega 1, 2, we can, of course, write that very similar as the same kind of equation, but this time with like the Gauss curvature of the original surface S. So that's the using the structure equation or the Gauss equation on S. So Gauss equation. So that's the left-hand side, gives us the Gauss curvature of the surface, which is good. Now we have to say, let's see what happens to the right-hand side. So the pullback of the right-hand side, which is k bar theta 1 wedge theta 2. So we have to now apply that we can have the pullback of a function times a form. We just plug in the function into the function that we pull back, and then we have the pullback of the form. So now we use the trick that we know that we can interchange F with the wedge product. So what we get here is minus K composed with F times F star theta 1 theta 2. But now we can use 0.2 to say that these ones are exactly the one forms that we get our fundamental dual forms. So that's 0.2. We get that K composed with F equals to theta 1 wedge theta 2. So now we calculated the right and the left-hand side on two different ways. And there was equality between them, so the result is we get also equality between what we calculated. The upshot is that minus K of phi1 wedge phi2 equals to minus K bar of F composed with phi2. Okay, but so we're almost there. So the only thing that ruins a little bit our fun is that we have theta1 wedge theta2 here on both sides. So we would like to get rid of them. And the easiest way to get rid of them is we apply E1 and E2 to this equation. What we get in this case is minus, what we use here is that theta1 wedge theta2 applied to E1, E2 equals to 1. Because phi1 eats E1 gives us 1, and phi2 eats E2, theta2 eats E2, which just gives us 1. And if you turn them around, then they hit like the opposite one, which just gives you 0. So it's 0 minus 1 minus 0. So if you apply E1 and E2 to this equation, what you get is that these terms just vanish with like giving you U1. And what you end up with is that K equals to K bar of F. So that's exactly what we were set out to prove, is that once you have the Gauss curvature of a surface and you have a local isometry, you take it back, you get the original Gauss curvature of your surface. So that's the proof of the Gauss theorem. So you see, essentially, it's just understanding what happens to the connection form and to the dual tangent frame under the pullback of an isometry. That's like step 1. And then the other equations, which are like really more important, are actually the structure equations, which tell you that you determine completely the connection form once you know that, like the theta1 and the theta2. So that's the important ingredients. So some remarks on the Gauss theorem. So the remarkable fact fact is that K only depends on the first fundamental form. And not on the second fundamental form. Although the definition, although we have K equals to, like K here is defined as the product of the principal product of the principal curvatures. And the principal curvatures are the eigenvalues of the shape operator. In different words, the eigenvalues of the second fundamental form. Which clearly depend on the second fundamental form. So it's like this bit strange thing. It's like you have like K1 and K2, the principal curvatures, they depend on the second fundamental form, they're the eigenvalues of the operator at each point, then you take the product that like a priori doesn't tell you anything about reduces any dependency, so they also depend a priori on the second fundamental form. But our discussion here shows that quite surprisingly, if you take the product, then you end up with something that actually doesn't depend on the second fundamental form, but it's something that is intrinsically and nicely defined just in terms of the first fundamental form. This whole observation is actually the start of a whole new field of mathematics. So that's gives rise to the field of what is called Riemannian geometry. So it's if you look at the proof that we did, it's what we started with was we have our surface, we choose a tangent frame E1 and E2, and the only property that E1 and E2 had were that they need to be orthogonal with respect to the first fundamental form. So that was all the ingredients, and then from that we derived the dual frame and we derived the connection form. And the idea of Riemannian geometry is to take that to the extremes, where we say okay, we have some object, and on that object we have defined something that is the first fundamental form. And then once you have this form, which is called a metric in this case, you study that object in itself. You completely ignore that this object, the surface, or higher dimensional things, sit inside another space where you have a frame around it. So you really just start with E1 and E2, connect, have some metric with, or some distance, the first fundamental form, and you completely ignore that there is something like a second fundamental form. So you try to kind of study the surface very intrinsically, without any reference to the second fundamental form. So, which has the point of view. For the Gauss curvature is E1 and E2, which perform normal with respect to the first fundamental form. So all we need is the surface and some notion of inner product of tangent. So that's the main idea, is that all we need is the surface in itself and some notion that we say okay, this vector is orthogonal to this vector. Once we have that, we can essentially reproduce the whole same proof as we say okay, we have E1 and E2, they give the dual frame, the connection form, and then we calculate the Gauss curvature. So that's the start of if you wonder how is this whole theory generalizing, for example, to three-dimensional objects or to four-dimensional objects or even higher dimensional objects. It's essentially taking this perspective of saying, okay, let's start with just the object that we would like to study and some notion of a dot product between the tangent vectors. So that's the idea. And that gives us a notion of intrinsic curvature. So the two-dimensional case is simple because essentially there's only one function that is like intrinsic. If you go to higher dimensions, it turns out to be like very complicated, and you have a lot of different functions that measure different curvatures in different directions. But like since we essentially have like E1 and E2, there's only one function that relates that. So like in two dimensions, it's only the Gauss curvature, but in higher dimensions, it might be a bit more complicated. But that's intrinsic, independent on how the surface sits in R3. So just saying like there is like a surface, and we don't have to worry about like how to visualize it in like an ambient space. And that's quite important if you think about like, for example, physics. Like the most profound theory of like gravitation that was developed by Einstein in the beginning of this last century, said that essentially it's like that the curvature of space-time is determined by the mass of the objects that are living in the space-time. So if you have like a black hole, then it kind of like gives like a certain curvature of space and time. And that curvature then gives you some force of particles that are like moving on the space and time. So that's like the idea of the general relativity here, that like the mass of the object gives you some intrinsic curvature. And like we are like ants, we live in the universe, right? We can only measure things that like we can like measure intrinsically of the surface. We don't know if there's like some 8-dimensional space where we can like view the universe as like nicely embedded, and there might be some aliens living in 8 dimensions that take a movie of like our universe and then know, okay, maybe they have like some curvature that relates how this universe is like embedded in 8 dimensions. But we really just like live in our 3 dimensions plus one space, one time dimension. So we can't measure something that is extrinsic. We can only measure things that are intrinsic to us. So the only thing that we can measure as like ants living on the surface is like something, the Gauss curvature. We can't measure the normal curvatures. We can't measure the principal curvatures. The only thing that we can measure is the Gauss curvature. So that's just like as some motivation why you might want to take another differential geometry class, which is usually called, and the following one would be called Riemannian geometry, where you study essentially higher dimensional objects like 3 and 4 dimensional surfaces, and then say like, okay, what is the notion of curvature, and like how are they defined, and like how do you make sense of like, for example, frames in higher dimensions and things like that. So that would be it's not something for this course, but that would be a course that you might like want to take if you're interested in geometry. And that gives you some applications in physics, in particular to general relativity. A bit more down to earth, the Gauss theorem also gives you some nice ways to calculate the curvature. The Gauss curvature to be exact. So. Calculate the Gaussian curvature. So like the way you would do that is that instead of really calculating the Gaussian curvature of the surface, you try to find like a surface that you already know the Gaussian curvature of, and find a local isometry between the surface that you want to study and the surface that you know. And then the Gauss theorem tells you, then you know immediately how the Gauss curvature of that one surface is related to the other one. So that's the one way to apply the Gauss theorem in applications. It's easy. And I give you an example of that after the break, how it looks like. In a different way, we can also use it like in an opposite way. Namely, the Gauss theorem can also be used to say that, to maybe determine if two surfaces are locally isometric, which is actually not that easy. Like if I give you just two surfaces abstractly defined, and I ask you, okay, are these two surfaces locally isometric? Like one way to do that is like, okay, maybe you find like a local isometry and then you can say yes. But how do you, for example, show that they are not isometric? If you get like the idea that they are really different surfaces, how do you say like, okay, how do I prove that they are not locally isometric and I'm not just like not able to come up with a concrete formula for the isometry? And one way would be to use the Gauss theorem. You calculate the Gaussian curvature of both of the surfaces, and then you say like one of them might be constant, the other one might be not constant, and then you say, okay, like yeah, clearly they can't be the same. So for one example, what we can apply that directly is that the plane and the sphere are not locally isometric. So just by calculating the Gauss curvature of the plane has k equals to 0, and the sphere has something which is strictly positive depending on the radius. So the Gauss curve can never be the same, like under isometries, like because like isometry would like put like the 0 to something not, positive. So they never can be isometric. So what this means is like very relevant for applications. If you have the sphere and you would like to make like some map of the Earth and say like, okay, like here is a piece of the Earth and I want to show that in an atlas, as you know, maybe it's from your school classes at the, where you had like really nice maps of the Earth. What this result is saying is that you cannot do that without distorting the distances. So whatever map you have of some part, even like a small part of the Earth, you always have to distort some distances, otherwise you can't depict like the metric. Like you can't depict the sphere as, or like a part of the sphere in a plane, because they are not locally isometric. So whatever you choose, either some dot product between two vectors have to change if you depict that in some chart. So you have to distort like something of this field. Like the measurement of distances and like angles can't be the same on the plane, like in the book and on the reality. And then last one, and you can think about that. It shows how to properly eat pizza. So after the break, we will discuss how the Gauss theorem is now related to this question that I had at the beginning of like how to actually eat the pizza without like the parts slowing down, and why that has some connection to the Gauss theorem. Okay, so let's make a break of almost 50 minutes. So we continue at half past.
So the Gaussian curvature only depends on the matrix.
Yes.
Or the inner product.
It's called metric, but it's inner product. It's called Riemannian metric.
But we only use matrix if two surfaces we have a same matrix on them, and we can get the same Gaussian curvature.
Yes, so like to be precise, like the first fundamental form.
But the first fundamental form is inner product.
Yes, yes.
And we can use an inner product to induce a matrix, but we can not use a matrix to define the inner product. So if we only have the same matrix, can we say the Gaussian curvature is the same?
No, you can, no, because you can change the angles, right?
But we have a proof. It's we find the matrix ES equals to this, and we finally get this equation. It seems that not depends on the inner product.
It's called a metric. It's an inner product. It's called what is called like it's called just like it would be we call it Riemannian inner product, but it's called a Riemannian. And the book says like it's a metric and then writes or something. Then it's actually an inner product. Like it depends. Of course, you can assume that they are always equal. For us, it was always again, it's something that takes like that's actually one of the stuff. Okay, but something of
The definition, the control on the 1, 2 doesn't depend on the inner definition of the inner function.
It does, because we need from the category 1 and 2, we need to be orthogonal with respect to the first one. So that's why we need
the inner product decide what is the orthogonal.
Yes.
So that the inner product depend on the
yes. Yes, but not like direct. Like it depends via this notion that we need to start with the 1 and the 2 which are orthogonal. Otherwise, you need to change the equations. Okay, let's continue. Like, where are my the slices of pizza? Do you, like the pieces of paper that I give? Like, are they somewhere like in the back or like the? Please. Yeah, want to get my pizza back? Yes. Thanks. Thanks. Okay. So before we come to the pizza, I first want to show some application of the third point that we had, like an application where we say like the Gauss curvature can be used to calculate the Gauss curvature of a surface that we don't know. So for example, this one, which is called like the catenoid. So that's like something that looks like a nicely rotated surface. So it's a surface, what is called a surface of revolution, where you just have like a graph and you turn that around. That's relatively straightforward to calculate the Gauss curvature of, and I think it was even one of your homeworks to calculate the Gauss curvature. This surface is called the heliozoid, so it's like something that's like a helix. So if you just trace like the outer points, it goes around and then it goes like infinitely times like up. So that's what is called a helizoid based on the helix. So both of these objects look like very different. And say like we would like to calculate the Gauss curvature of this object. You would have to set up the coordinates and you have to like calculate, and at some point you get something. A little bit more interesting would be to say like, okay, I know the Gauss curvature of this object, and let's construct a local isometry to this object here. And then we know, okay, at points which were like, for example, this point would maybe correspond to say like this point. And then you know that the Gauss curvature of this point here is the same thing as the Gauss curvature over here. So that would be one way to very straightforwardly get like the Gauss curvature. So you only have to say like what is the isometry, and I don't want to like talk too much about like formulas here, but give you some geometric idea how to do that. Like what you have is like you have this catenoid, and you take your scissors and you cut it in some line. So that's like what is shown here. You have like a cut, and then you start to slowly move one of these elements slowly up and slightly twist them as long as you go. So it's like you kind of like untwist them and like you stretch, and like you not stretch them, but you just bend them, you rotate them essentially and translate them. So because it's like from step to step, it's like more rotation and a little bit of translation. That's like a nice isometry. And the isometry like translates what you started with, the catenoid, into this helizoid, or if you go it other way around, the helizoid back into the catenoid. So that gives you one way to say like what is the Gauss curvature of a point. You just take the same point over there, and then you say the Gauss curvature of both of these points have to be the same. So that's like a very powerful tool, especially if you don't like understand a certain surface quite well, but you know that it comes out of like some twisting also. So now it's time to lift the question of like how to eat pizza. So that was actually last year. I made like asked the AI to generate this picture. That's why you see like the finger is like a little bit not so good. Yeah, so I guess you get the idea. It's like, yeah, that's usually what happens. You just like try to eat your pizza and then you have to try to catch it. Or you eat it like very gentleman-like with two hands. That also works if the pizza is like big enough. But what do you do if you just have one hand free and want to eat pizza properly? So who wants to show how it's done? I think many of you had it already. So. Yes, so it's easy to do, right? Like you just like bend like both of these ends, you bend them upwards, and then like the thing is not going down. And just like by bending here, like it's not like that I have my finger like stretched until there. It's like just bending these sides here, for some reason prevent that this one is like tipping over. So why is that? Who can explain that? Like it's clearly related to the class, right? It's like curvature. So what is happening? Why is it like if I bend that like upwards, why does this don't want to go down? Yes, but right now the Gaussian curvature is not zero, right? the Gaussian curvature of this object is not 0. You mean because of this? Okay. And then, but this one is also 0. So why can't I go from this Gaussian curvature to 0 to this Gaussian curvature to 0? Yeah, so the point is that if you start with the flat paper, so like you start like say here, and you just bend it, then what happens is that it's like both times has like Gauss curvature 0. So what we need like from physics, the input from physics is that if you have a flat object, what is like easy to do is like local isometries. Like it's very easy to bend it. Like it's very easy. Like you don't need like much force to bend it. And like so bending is very easy. But it's always like a local isometry. It's very hard. Try to stretch the paper. It's very hard. Like you need like a lot of force, and you just rip the paper apart. So like bending is easy. Like local isometries are easy to do. What is very hard to do is like not isometric things. And now imagine just like that you have this object, and you would like to do an isometric to this object where you like have this kind of like curvature goes up, and at the same time this one would go down. It would be something that has like non-Gaussian curvature 0. So if this one bends, like if you have something like that, then you have like a curvature in this direction and a curvature in this direction. So the Gauss curvature would be non-zero at some point, because like the principal curvatures at some point would be both times not 0. So in this case here we have Gauss curvature 0, and if that would be bending downwards, then it would actually like change the Gauss curvature. So so that means by our Gauss theorem, it means this procedure from like being in this operation to now putting that one down cannot be an isometry. So it has to stretch something in the paper, and that costs a lot of energy. And that energy is like, like either it's like heavy enough, like this object that I put at the front, and then it also puts down. So like that's why if I do that, and it still flips over. So if you give it enough energy, then it overcomes it. But you need like more energy than just like this operation here, which is a local isometry, because like it's flat, has Gauss curvature 0, and now it bends over, and it still has Gauss curvature 0. So that's like an operation that is like everything is isometric, and that doesn't need much energy. So it's really like this point is like that. If you have like physics tells you, at least for thin sheets of objects, it's like local isometries are cheap and like easy to do, but like stretching and non-isometric things are hard to realize. And that's like combined with the Gauss theorem tells you how to eat pizza. So that's one application. This observation, you can push that like way further and like say like, okay, now we know that something gets like a lot of stability just by curvature. Like putting some curvature in something in one direction gives you stability in something that is like in the opposite directions, right? So like I put in curvature in one direction, so this one is easy to do, right? Like it's just like taking this sheet of paper and just putting a bit of curvature in there, and then what I get is like stability in the opposite direction. So like here's the curvature direction, and then I get like stability in this like opposite direction. And that's, for example, what can be used in these card boxes. If you get like a paper from Taobao, a package, then like it's very thin material actually, but it's very stable. You can put like these boxes on top of each other and move, and that's like still works. And that actually comes back to having like the inner structure, which is just like some small bendings, and then what you get is like it's very hard to now bend it over in the opposite directions. So it's very hard to like put now something in this direction of curvature just by putting some like very simple curvature in there. And here we have an example from architecture. That's a nice place in Valencia in Spain. It's a museum. And you can see it's like the same principle. It's just like the pizza on its head, so to speak. So what you have here is a pizza. You bend that over, and then you get this kind of shape. And what you have is now that it's like instead of like the gravitation is pulling this one, it's like now we have the stability that this one is like the gravity is like pulling downwards, but it's very stable. It's not like you need a lot of force on the tip to actually bend it over. And that's why you can reach relatively far surfaces that stretch out very far, but just like bending or giving it some connection in some of the opposite directions. So that's like one of the really important applications of curvature and like the stability that you get like directly from the Gauss theorem, combined with this insight in physics that like isometry transformations are usually cheap to do. Non-isometric things are like very expensive or cost a lot of energy or force. So that gives you some nice applications in the direct world for like something important like as the Gauss theorem. Okay, so that's like some applications of the Gauss theorem. I would like to discuss some more applications for today in mathematics, where we can like, I think that's like not for me. It's like quantum field theory, also very interesting. So I would like to discuss some applications of the Gauss curvature to rigidity in some ways of surfaces. And I want to give you some taste of that. And the idea here is that maybe like going back to the analog to the curves is like a good idea. So in the curve example, what we saw is that once we give you like the two functions, namely the function of the curvature and the function of the twist, the kappa and the tau, once I give you these two functions, you can always reconstruct the curve from that. So that was like this reconstruction theorem from curves that tell you essentially curvature and twisting gives you the curve back. So you can now think about like a net logical question would be, what is the analog of that construction for surfaces? Where we say, okay, we give ourselves, say, the Gauss curvature, can we reconstruct the surface? So I give you some complicated function, can you construct the surface back from that? And usually the answer is no. Usually you need more information than the curvature. But sometimes, if you put a little bit more information in there or like have some particular settings, you can actually say quite a bit. And that's like an example. Construct